Hello, once again, this is Mr. Wakefield, and right now we're looking at section 2.7, getting near to the end of the chapter 2 packet here, or the packet that has chapter 2 in it, rather. You can see here we've got like 10 different rules here, and it talks about stretching and reflecting graphs and vertical and horizontal shifts of graphs. Okay. I used to teach it this where I would teach all these different things, but then I ended up finding a way that I think is better for students. There is a one set way that you can do all these different types of things, and it doesn't work on every single graph on the whole world, but it will work on all of the graphs that we see here in this section. And it does work on almost every graph in the world, as a matter of fact, as well. So I think it's best to look at that more simple way of doing it. So these are all legitimate. It's just that there's a better way, and it's the way that I'd like you to do it because I think that you'll like it and it'll be better for you. That way is this 5-step method I have on the back side of the worksheet. Okay. And what it is, again, is, as I mentioned on the front of the sheet there, it involves taking a graph and stretching it out, making it wider, skinnier, maybe flipping it upside down, that kind of thing. And you're going to see here as we go down to the bottom here and look at the first few problems. We saw earlier in the last section, as a matter of fact, we saw x squared, okay? You can see that all of these are slight variations of that. X squared plus 3, x squared minus 5, 2 times x squared. Okay, here's the thing, you guys. If you have a graph or a function that you're eventually going to graph anyway, that has a variable, it doesn't have to be just a variable, but it has something with a variable in it being squared. In this case, yeah, the x is being squared. The x is being squared again. Same thing with 3 and 4. In 5 and 6, you have not just x, but x plus 3 being squared, x minus 5 being squared. If you have something with a variable in it, whether it's just x or if it's something with x in it being squared, okay, then what happens is that means that it's going to build off of this basic graph that we saw back in section 2.6. And so how does it build off of that? Well, that's where we're going to talk here. But I do want you to, in fact, let's go ahead and look at that first step here of the 5-step process that I want you to do. Okay. In fact, it says here in the directions, graph using the 5-step method listed above. Okay. I crossed out the words on the previous page because ever since then I've condensed it down to being on the same page. So it's the 5 steps that you see listed above here. This is the 5th step right there. These 5 steps, okay, 1 through 5. And so now, how do we go about that? Well, the first step says is start out with a basic graph and its 5 basic points. So like I said, when you have x being squared or something with x in it being squared, that means that we're going to use the x squared graph. Okay, just as a comparison, if you had something with x, if you had x being square rooted in your function or something with x in it, as we'll see on the back of the worksheet, being square rooted, okay, then you would use this one. All right, but now we're going to be using x squared. All right, so that is the first step there, is to decide which one of these 5 graphs, which one of these 5 basic graphs from section 2.6 are you going to use. And that's why it says here, see the 2.6 worksheet to figure out which one of the functions that you're going to use. Which one of the basic graphs are you going to use? It says then take the 5 basic points, or if it's the square root function, since they only have 4 basic points, you use those. But here it's talking, and when they say 5 basic points, they are talking about these 5 x values, not the y values, because those are going to change, but the 5 x values right there. All right, now if you have a situation where the thing that's being square rooted is just the variable x, and it's not like x plus 3 or x minus 5, then you can actually skip steps 2 and 3. Let me tell you why. It says here, it says figure out what expression replaced x in the basic function that you chose in step 1. Well, If it's still just x being squared, just like it is in the basic graph right here, again, the basic graph is x squared. Let me bring that back up here. The basic graph is x squared, and here the x is still being squared. When it's still the variable being squared, you can skip those two steps because that's where they talk about what happens if something else is being squared. Now, in problem number 5, for example, because it's x plus 3 being squared instead of just x, that's when you got to do steps 2 and 3, okay? So we're going to skip, for this problem, we're going to skip all the way down to, actually, let me write out step 1 first, excuse me. Step 1 first is to realize that we need to use this basic function here. We decided that that was going to be the one that we were going to do. All right, now, step 4 then, as long as we're going to jump down to that, is here. Then actually, another thing in step 1 that I need to remember to say one more time here, is not only do you choose the x squared, but you choose all of the x values from the 2.6 list that we had, the 2.6 list of basic graphs. You take all of those and you transform them from this page right here in 2.6 and bring those over here. But do not bring the y's over. Like I said, those are going to be the ones that change. Okay. Now, all you got to do at this point, and this is what step 4 tells you to do, is just simply plug those 5 numbers into the function. Not the x squared. That's where it's building off of, but that's not where the final answer is coming from. No, we want to plug it into here because that's what we're ultimately going to graph. Okay, so if you plug in, say, -2, just to give you an example here, -2 squared plus 3, that's equal to 7, isn't it? You can see that there. So that means that -2 is going to pair up with 7. In a similar way, if I plug in -1 squared, and then plus 3, okay, that would give me 1 plus 3 equal to 4, wouldn't it? Okay. And so that means that -1 pairs up with 4. If you do that same thing with all 5 of them now, 0 squared plus 3 is going to be 3. Looking at this one now, 1 squared plus 3 is going to be 4 again. And then finally, 2 squared plus 3 is going to be 7. So I'm now going to plot those 5 points, okay? It's going to go a little bit off the page here, but not that far off, so I won't change the scale of the y-axis here like I did on a problem not too long ago in a previous section. I will go ahead and, in fact, I did that in the last section on one of those problems, but this just goes up to 7, so that's fine. Here's where the points are. Let's plot them. 0, 3, 1, 4, 5, 6, and you know what? I went up too far, didn't I? Hold on. 3, just want to make sure I'm counting this. Oh, you know what? I'm sorry. I plotted that wrong. I put it one spot too low right there. One spot too low. So here's the 3 right here. That's what was wrong. And then here is the 4. 1 comma 4 is right there. And then 2 comma 7 is right there. Okay. And then the other 2 points, -1 comma 4. Oh, I did it again. Sorry, guys. There it is right there. And then finally 2 comma 7, or pardon me, -2 comma 7. And here's the thing, you guys. Now that you got the 5 points on there, okay, it's going to be the same shape as it was here. It might be a little bit skinnier. It might be a little bit wider. Sometimes it'll be flipped upside down or spun around. But as you guys know, if you flip something upside down or spin it around, it's still the same shape, isn't it? Okay. Now, if you do make something wider or skinnier, what I mean by that is, and that's not going to happen here, but what I mean by that is sometimes it'll look something like this. Okay. Sometimes it'll look something like that, a little bit skinnier than this one. Sometimes it'll look something like that, okay, where it's much wider, all right? But it's still that same basic bowl shape that is otherwise known as a parabola, okay? and then it just comes in different forms like that. So it still has that same bowl shape. All right, what else is true about a parabola as long as I'm talking about that? It is the same width on both sides, okay? See how if you take the point where it's at the bottom here, that's called the vertex. And if you cut a line through that vertex right there, both sides of that, in this case that line would be the y-axis, both sides of the vertex there they look the same. Okay, here's what a parabola is not. Okay, if you got something like this and then you got something like that, all right, right there, that's not a parabola because the vertex is this imaginary line right here, and one side is skinny and the other side's wide, isn't it? Okay, so a parabola looks the same on both sides, and that's what I want to make sure that you remember. Okay. So let's go ahead and draw that basic parabola shape then. Another thing about parabolas that you need to remember is that they have what? They have arrows on both ends of them here. Okay, that again doesn't, since it's the same basic shape, it's still going to have those same two arrows on each end. Okay, and like I said, both sides of where the vertex is, which is the lowest point. If it's going upward like that, the lowest point will always be the vertex in that case. Both sides should be just as skinny or wide as each other. Okay. So let's keep moving here on the next one here. Very similar thing. If I again, just like in all 6 of these problems on the front side of the worksheet, is since we're squaring something, we're going to use the x squared graph once again with its 5 basic numbers here, 5 basic x values. Sometimes those x values are going to change. We'll see that when we have to do steps 2 and 3 down here, and number 5 will be the first time we got to do that. But here, you don't have to do steps 2 and 3. Why is that true again? Just like in the last problem, it's because it's when it's just the variable being squared as opposed to x plus 3 in problem number 5, that means that you just keep these 5 numbers the same. You don't need to like change them at all, okay, which we'll learn about later. Sometimes we do. So if we plug in these 5 numbers, what do I get? Again, just as a visual here, negative 2 squared minus 5. And you just plug in the other 4 numbers the same way. Okay, that would be negative 1, wouldn't it? So negative 2 would pair up with negative 1. If I plug in negative 1 in the same way, I'm going to get 1 minus 5, which is negative 4. If I plug in 0, 0 squared minus 5 is going to be negative 5, and then so on. Let me do the last 2 here. It's going to be negative 4 and negative 1. Okay, so let's plot those 5 points right here. 1, 2, 3, 4, 5 right there. Okay, that's where 0, negative 5 is. Okay, now we get those 5 points right there. And as you can see, this parabola looking type shape is starting to materialize once again. All right, it's pretty clear what's going on. You can tell that this is the vertex here. Not a surprise because the 0, unless that gets changed, or actually, you know what? Let me not go too fast there. I don't want to get into that just yet. But yeah, the 0 is going to be the vertex. You can tell that just by looking at the graph. We'll get into more detail about how you know exactly, or how you can be absolutely certain, and not just because it looks like it, but how you can be exactly certain that you know where the vertex is. Okay, and so there you go. All right, so that same basic shape. Okay. Once again, in problems 3 and 4, the same thing's going to happen. All right. Not only are you going to use the x squared graph again. All right. Going to use x squared again, f of x equal to x squared, but you are going to use the same 5 points from negative 2 all the way up to 2 because it's the x being squared there in the problem, not the 2x. If the 2x was being squared, you guys, that'd be different. but the 2x is not being squared because you don't have a bracket there. Remember, when you have an exponent next to a variable, if there's no bracket between the x and the 2, only the x is being squared and not anything in front of it. So it is still just the same variable being squared, and that means that these 5 numbers here will stay the same. Okay. So what do we get when we plug in those numbers? Again, I'll just do one here just so we can visualize it. Exponents come before multiplication, right? So we do the exponents, that's 4. 4 times 2 is 8, right? And when I plug in -1, I get 2 times -1 squared, which is going to be 2 times 1, exponent first. 2 times 1 is 2. 2 times 0 squared is going to be 2 times 0, which is 0. 2 times 1 squared, again, is going to be 2, just like -1 was. And then 2 times 2 squared is 2 times 4, again, and that's going to be 8. All right. So if I plot these points here, and I just, you could change the scale on the y, since the 8 is kind of like way up here. But I'm not going to do that this time, you guys, because I want you to really see how sometimes these graphs get stretched out and they get really skinny, all right? So it's okay to do that theoretically, but just for the sake of showing you something here, I'm gonna just keep the scale the same way. So I'm plotting these points here, 5, 6, 7, 8. So there's 8 right there. Let me get these now that we've shown that already. Here's where 8 is, right? So if I plot those, I get that right there and this one right here. Now, very important thing, we can all see what the parabola is doing here, right? It's just a skinny version of a parabola. But it is very important that you realize that parabolas are smooth. Smooth, you guys. It is not, there's no sharp turns. Okay, do not make this look like a V shape right here where it just suddenly changes direction. I know it's hard to do that because it's so tight and skinny like that, but you don't just make it a V shape right there. There's another type of graph involving the absolute value where it does do something like that, but that's the absolute value. This is not the absolute value. So it is important that even at the vertex, but everywhere on a parabola, it moves in a smooth manner with no sharp turns. Okay, the absolute value, just as a comparison, the absolute value, that's when it makes that sudden sharp turn like a V shape, right? Okay, think of it this way. Parabolas are U shapes. Absolute values are V shapes. Okay, this is a parabola because it comes from x squared. So it's got to be a U shape. So again, I know it's kind of hard to do that, but see how I'm doing that here? I'm just being really careful to make that look like it's smooth right there. And then we just finish off the parabola. Both sides of the vertex look the same width, okay? Like I said, it's smooth, and don't forget to put your arrows on both ends there. Okay, so that's number 3. Moving on down here to number 4, we see that again we're squaring something, so we're gonna base this off of the x squared once again. All right. On the back side of the worksheet, we'll see other types of graphs besides the x squared being used. But again, really careful. You guys got to realize, since there's no parenthesis between the x and the 2, it is just the x being squared, not the negative x. And since it's just the variable and not the negative that's being squared, we use the same 5 numbers, -2 all the way up to 2. We use those when it's just x, not negative x, not 2x, okay, not x plus 3 like in the next problem, but just x being squared. All right, so once again, we just plug in those numbers because you can skip to steps 2 and 3, and we can go right to step 4, which, as you'll see at the top of the page there, it says just plug those 5 x coordinates that you have right there, just plug them in to the final function here, not the x squared, but the one that we're ultimately graphing here. If we plug that in, remember, Negative x squared, you guys, means negative 1 times x squared. Negative 1 times x squared. Anytime you got a negative at the beginning of an expression on that side of the equal sign, it means negative 1 times. Okay, and you know that that's a coefficient of negative 1 there anyway. And coefficients get multiplied by the variable. And so this is all not a surprise. Negative 1 times x squared. But because of that, we got to be really careful with our negatives here. Remember to plug in the negative into the x. The negative 1 is separate, and so it's negative 1 times negative 2 squared. Exponents come first, so we get negative 1 times 4, and that, of course, is negative 4 right there, right? Okay, so we do that same thing with all of those other 4 numbers. Excuse me. And so doing that, we get, again, negative 1 times, and this time I plug in negative 1 squared, and that gives me negative 1 times 1, which is negative 1, okay? And so we keep on doing that on all of these. Negative 1 times 0 squared is negative 1 times 0, which is 0. Negative 1 times, and then we plug in 1, that's going to be negative 1 times 1, which is negative 1. And finally, if I plug in 2, all right, I get negative 1 times 2 squared. Similar to this, it's negative 1 times 4, which is negative 4. Okay. Now, what this is going to lead to as you graph these 5 points right here is it is going to lead to something that's going to look like a parabola, but it's upside down. It looks like somebody took a regular looking parabola and just flipped the thing over. Okay, it's still going to be the same shape. Don't be alarmed if it flips over, all right? That is a possibility, and so don't worry if that happens, all right? Just as long as you did all your calculations right, that's not something that's unusual. So what's important is that you still draw the same shape here, all right? You still have it look the same on both sides of the vertex. By the way, when it's flipped upside down, the top number is now the vertex. When it's right side up like this, then the bottom point is the vertex. And that's important to know where the vertex is because like I said, both sides of the vertex have to look the same, all right? In other words, if one side's skinny, the other side's got to be skinny. If one side's wide, the other side's got to be wide, okay? And so there you go. Don't forget your arrows as well, like we talked about. All right, now finally we're going to see a problem here where we see what happens when it's not, and again, something's being squared here, so that hasn't changed. All right, we're still going to do the x squared basic graph from section 2.6. We're still going to base it off of that, you guys, but here's where things get different. The thing that is being squared, since you picked x squared, you have to ask yourself, what's being squared? All right. What is being squared here? It's not x this time, but because we have a parenthesis next to the exponent, that means that the thing inside the parenthesis, which is x plus 3, that is the thing, you guys, that is being squared. Okay. Now, I wanted to pull out, oh, here it is. I think this is it. Nope, that's not it. I wanted to just check something here real quick. Let's see. Oh, here it is. Okay. Just give me a moment here, guys. But as I'm retrieving that, again, because the thing that is being squared is not x this time, we need to realize that we need to do steps 2 and 3. Step 2 says, figure out what expression, zoom out a little bit, figure out what expression replaced the x. In other words, if the x was being squared in the basic graph, all right, what is now being squared in the graph that you're ultimately supposed to do here? Okay, well, it's x plus 3. So if you're doing x squared, you have to ask yourself, what is being squared? If it's still just x like it was in the first 4 problems, then it didn't change, and that's why you don't have to do step 2. Okay, or step 3 either for that matter. But if it does, then you have to. It's a much more involved situation. So here's what you do. Since there's 5 basic numbers, you guys, we're still, and make yourself a little bit of space here, okay? But I'm still going to write down those 5 numbers, but make a little bit of space here to the left of that. There's a reason for that. All right, here's what we're going to do. The x plus 3, if the x changes to x plus 3 like that, then that means I'm going to write down x plus 3 for each one of those 5 numbers, okay, and I'm going to make an equation out of, sorry about that, there it is. Let me zoom in again. I'm going to make an equation out of those 5 things right there. So in other words, you write down the original 5 numbers from the basic graph, okay, that you saw in section 2.6, and then you take the x plus 3 and you write it down 5 times and make 5 equations out of that. So this is the what? This is the old x values right here. This is the old x values, -2 all the way down to 2. We want to then find out right next to that there the new, I meant to say new x's, okay? The new x values. What are the new x values? The way to figure out those new x values is to solve each one of these 5 equations. Now, as you guys know, when you have x plus 3 equal to a constant, you just need to subtract the 3 over to get x by itself and solve that equation. So whatever that ends up being equal to when you get x by itself, that is what you put here in this column. So if I subtract the 3 over, I'm going to get x equal to -5, aren't I? If I subtract the 3 over again, I'm going to get -4. Do it again, I get -3, and then a couple more times I get -2 and -1. So I solved each one of those 5 little equations, and this is what I get. Okay, that was step 3. Yeah, that was step 3 where I actually picked the x plus 3, picking x plus 3, realizing that that's the thing that's being squared. That's step 2. Step 3 is to do this whole process right here of changing the old x's to the new x's. By doing this right here, where you set the x plus 3 equal to that. In the next problem, you're going to do x minus 5. It's going to be exactly the same thing, but now it's going to be x minus 5 written a whole bunch of times here, and then you do the 5 numbers, and then you solve those 5 equations. Okay, but let's finish this off first. What you do in step 4, like always, is once you figure out what your x's are, and they changed, all right, but now we're going to figure out what the new y's are. And we do it the same way we did before. You just simply plug your new x values into the function here, and it is going to give me my new y values here. All right, so if I plug in, say, -5, okay, it's going to be, isn't that -2 squared, which is 4? Okay. And so you do the same thing on these other 4 numbers here. -4 plus 3 would be -1, and then you square it, you get 1. If I plug in -3, -3 plus 3 is 0. Remember, you got to do parentheses before exponents. -3 plus 3 is, is equal to 0. 0 squared is 0. And then if I do the last 2 right here, I'll end up getting 1 and 4. So these numbers here are the ones that you graph because they're the new ones, okay? Those are the new ones. And so let's graph those. What do we get? -5, 4 would be where? That would be right 1, 2, 3, 4. Okay. -4, 1 is right there. -3, 0 is right there. And then the last 2 here. You can see that once again, not a surprise, because it came from the parabola x squared function from 2.6. Not a surprise that the shape looks like that. And so let's go ahead and draw that same shape. Again, make it look the same on both sides of the vertex. Where's the vertex this time, you guys? It is at the bottom because the parabola goes up. It's always at the bottom and the parabola goes upward. And like in the last problem here, it's on the top if the parabola goes downward like this. Okay. Okay, number 6 here we got same type of thing here. Once again, you have something being squared. And so we're going to have, it's going to build off of the x squared function here. Okay. And now, just like in the last problem here, it is not the x being squared this time like it was in the first 4 problems, but just like problem number 5, we are going to have x minus 5 being squared because the bracket is being squared and x minus 5 is inside of it. So again, in step 3, we're going to have what here? We're going to have x minus 5, x minus 5, x minus 5, x minus 5. We're going to write that down 5 times because there is the old x values. There's 5 of them once again. -2, -1, all the way up to 2. Just like we've seen on all 6 of these problems here. Okay. So if I solve these brand new 5 equations that you see here, it's going to be what here? Okay. The new x's are going to be found by taking the 5 and adding it over to the other side to get x by itself. So -2 plus 5 is 3. -1 plus 5 is 4. And 0 plus 5 is 5. And then the last 2 are going to be 6 and 7, right? Okay. Moving forward now, we get the new y values. We need to figure those out now. Okay. And those are going to be what? Well, we plug these in. Anytime you figure out your new x values, those are the things that you plug in to figure out the new y values. All right. So let's do it. 3 gets plugged into here. 3 minus 5. Okay, and I'm okay if you don't actually write down the work here on this. You can do that. This is a small enough problem. If it was a bigger problem, that'd be different. But small enough. You just got a couple of computations there. -2 inside the parenthesis, and then you square that, you get 4. I just wanted to give you a visual here so you know exactly what I was trying to do here. If I plug in 4, I get 4 minus 5 is -1, and then when you square that, you get 1. If I plug in 5, I get 0 squared, which is 0. If I plug in 6, I get 6 minus 5, that's 1. 1 squared is 1. And then finally, if I plug in 7, I get 7 minus 5 squared, that's 2 squared, which is 4. Okay. Now 7 kind of goes a little bit off the page here, but not that far off, so I'm going to just kind of move it over here instead of changing the scale. Okay, so let's go and graph this here. We got 3, 4, 4, 1, 5, 0, 6, 1, and then 7, 4. If I then plot that, again, you can see that at no surprise, since it came from x squared originally, it is going to be what? It is going to be like this right here. Okay. Again, vertex is at the bottom. Okay. Both sides of the vertex look basically the same. All right. Arrows on both ends. All that kind of stuff, and make sure it's smooth. All right, a nice smooth turn, no sharp turns. Okay, so that is the front side of the worksheet. Let's start looking now at some other types of situations besides just x squared. Actually, correction, we got one more of those. All right, x squared is such a popular one to do. That's why I have so many of those examples. But we'll have some other examples here starting in number 8, as you can see there on the sheet. Notice again here that we have something squared. I want to back up here for a second, you guys. I want to make sure that this is clear. When I say that that you can just do this thing anytime something's squared. That's not quite exactly it. I want to make sure you don't get that confused for problems we do later on. We would not do this method that we're doing right now. Say in chapter 3, we're going to see something like this right here. Okay, 2x squared plus 3x minus 4 or something like that. Just because you see something squared doesn't mean you should do what we're doing right here. Okay, it's when you have something being squared, even if it's not just x, whatever that thing is that's being squared, if it's something that is has x in it, it could be like it could be what we call a degree 1 polynomial. That means that it could be like an x to the first term only. It could be x or 2x or 3x inside this parenthesis here, or it could be something like that is being added or subtracted to a constant. Okay, that's a degree 1 polynomial inside this parenthesis here. So if you have something being squared, whether it's the variable, like we saw in the first 4 problems, or if it's a degree 1 polynomial inside the parenthesis, if all of that is the case, and then on top of that you have that's being multiplied by something here. In this case, it's being multiplied by 1, and then you're adding or subtracting all of that to something else behind it like this. It's in those 3 cases, when you got the degree 1 polynomial here inside the parenthesis being multiplied by a constant number, not a variable. This can't be a variable on the outside. Being multiplied by a constant, and then it's being added or subtracted to a constant back there. When those 3 things are all true, and you can see that that's the case here in number 10, right? You got a degree 1 polynomial here, okay, just an x to the first in there, in other words, not an x squared inside of there, and then it's being multiplied by a constant, and then you're adding a constant to all of that. Same thing here. You got inside the radical. Just like when it's inside the bracket. If it's a degree 1 polynomial being multiplied by a constant, and then you're adding or subtracting, in this case subtracting a constant, that's when you can do these 5 steps. Okay, that's not the case here because the x squared is being multiplied by a constant, but it's not being, you have a variable being added to it after that, not just a constant. Like we had here where it's just the minus 3 after that. So there are some types of graphs where we got to do other things besides the 5-step method that we're learning here. Okay, so just wanted to talk about that, but let's get back to what we were doing there. Let me erase that off here so I'm going to have enough room to show the work that we need to see. So as you can see here in this problem, we have something being squared here, okay? That something has, the degree 1 polynomial, but it's something being squared, like we saw in the first 6 problems, and so that means we're going to base it off of the x squared again, one more time here. All right, the next 4 problems after that will not be like that, but we're going to base it off of that. Okay. Now, what is being squared here, though, now that we've established that it's going to be x squared that we base this off of? The thing that's being squared is x plus 2. So, again, we do all the same thing that we did in the last 2 problems on the front. All right? We write it down 5 times, like that. Okay. We take the old x values. We set x plus 2 equal to all 5 of those right here. Let me write it out. And then we solve those 5 equations to figure out the 5 new x values. What are they going to be? Well, as you can see here, in order to get x by itself, we need to subtract 2. So negative 2 minus 2 is going to be negative 4. Negative 1 minus 2 is negative 3. 0 minus 2 is negative 2, and then so on down the line here. And there we go. All right. Now that I have my new x's, I need my what? I need my new y values, don't I? Okay, what are my new y values? you need to plug in the -4 and the -3 and all 5 of these into the final function here in order to figure that out. So plugging in -4, we get, remember, parentheses first. So parentheses first would give me -2, and then we square that, it's 4. 4 minus 3 is 1. Let's do that again now with -3. I know that's a bigger problem right there. If I plug in -3, you guys, I get -3 plus 2 is -1. -1 then gets squared. That is equal to 1. But then 1 minus 3 is -2. And we do that with the other 3 numbers here. -2 plus 2 is 0. 0 squared is still 0. 0 minus 3 is -3. And then the last two here, if you plug those in, you're going to get -2 and 1. So once again, you guys, it's these numbers right here, the x's and y's, that you got to plot. All right? Where these are the x's and these are the y's. So 5 ordered pairs. Where are they located? Let's see. -4, 1 is right there. Okay, -3, -2 is going to be right there. There it is. -2, -3 is right there. You can see the parabola is starting to develop here. And then here's the last two right here. Okay. So once again, you can see that we got this right side up bowl shape starting to develop. We are absolutely 100% sure that it is a parabola, not something else that's similar to that, because it's based off of x squared, and so it has to be that similar parabola type shape. So therefore, I'm going to do the same thing I always do with a parabola: make it smooth, make both sides of the vertex look the same. Okay, and put arrows on both ends. Okay. Now, finally, let's look at some problems now, you guys, where we have different basic graph that we're going to look at. Since you have the square root of something, and in particular the square root, what's being square rooted is a degree 1 polynomial, like we said, with just an x in there, not x squared. And then you're multiplying it by a constant, 1. And then you're adding, I know this is kind of weird, but you don't have to write this down, but you're adding 0 to that, right? So if there's nothing there but just a square root, it still qualifies because you're multiplying it by a constant, and then you're adding a constant to that. So you don't have to write that down. But I just wanted to confirm that that's why you're allowed to use the 5-step method here. Okay. And all the problems in this section, you'll be able to use the 5-step method. I'm not trying to say that you're going to see anything different than that in this section, just later on. Okay. Now, let me make sure that I'm organized here. Okay, so in because we have something being square rooted, we're going to base it off of the square root of x function. Let me show you that. Okay, that's this one right here. It almost looks like, oh, sorry there. Let me bring that up for you. So it almost looks like somebody took a parabola, turned it on its side, and then cut the bottom half of it off. Okay, that's what it looks like to me anyway. All right, but that's what's going on there. And so when we draw the final graph, it's going to be that same basic shape. All right, but again, going back to the previous 7 problems, what do we always do? We always ask, since it was x squared, we always asked, what's being squared? X squared, what's being squared? Right? We asked that on all 7 of those. Now that we have the square root of x that we're using as our basic graph, we're not going to ask, hey, what's being squared? No. Instead, we're going to ask, what's being square rooted? Okay, what are we taking the square root of? It's not just x, it is 2x minus 5. And so that's the reason why I'm going to write down 2x minus 5 here. Not 5 times, but 4 times. Still the same idea, though, but it's just 4 times because we only use 4 basic numbers here for x, whereas in the other graphs we use 5. It's just the way it is with the square root of x. It's not necessary to use any more than that anyway. So you take the old x values that you would normally have if you were graphing square root of x, which are what? They are 0, 1, 4, and 9. You see that right there at the top of the 2.6 worksheet? All right. So I'm going to take those. All the same process here. You're taking the old x's and you're setting them equal to this thing that you chose, 2x minus 5, and you're solving that equation. Or solving all 4 of those equations, I should say. All right. And that creates the new x values. What are they? Okay, in order to get x by itself, we need to add 5 and then divide by 2, right? Add 5 and divide by 2. If I do that here, 0 plus 5 is 5. 5 divided by 2 is 5 halves. We'll talk about how to graph that here in just a moment. 1 plus 5 is 6. 6 divided by 2 is 3. 4 plus 5 is 9. 9 divided by 2 is 9 halves. And finally, 9 plus 5 is 14. 14 divided by 2 is 7. Okay? And so then that's going to lead to the new y values. The new y values. What are they? Well, again, in figuring out the new y values, you plug in the new x's into the final function here that you're going to use. That is what? If I plug in 5 halves and multiply that by 2, that would be 10 halves, which is 5. Okay. And remember, when you multiply by a fraction, all right, you make the 2 into a fraction also. And so that's why you get 10 over 2, which is 5. But 5 minus 5 is 0. And remember, you have to calculate the inside of a radical, figure out what it is, before you take the square root. Since it was 0, we then take the square root of 0, which is 0. Okay. So let me just give you a visual of that there. I kind of did that all in my head almost there. We end up getting 5 minus 5, square root of 0, and then that's where the 0 came from. Square root of 0 is 0. Let's do that again with 3. 2 times 3 is 6. 6 minus 5 is 1. Take the square root of that. Square root of 1 is 1. And we'll keep going here. 9 halves. 9 halves, if you plug that in, okay, you would get 18 over 2 when you multiply it by 2, just like you did. It'd be the same thing as this, only it would be a 9 here, okay, instead of a 5. So you get 9. 18 over 2 is 9. 9 minus 5 is... I'm sorry. I went too fast there. 9 minus 5 is 4, but I didn't take the square root yet. Okay, so the inside of the square root is 4, but then when I take the square root, it's 2. And finally, 7, we get 2 times 7 is 14. 14 minus 5 is 9. Square root of 9 is 3. Let's go ahead and graph this thing. When you graph fractions, you guys, please remember you can convert those to decimals. And then this is going to be 2.5, isn't it? If you put that in your calculator, you'll see that. 2.5, and then this one is 4.5. Again, I'm not expecting you to know that just by looking at it, but if you put that in your calculator, 5 divided by 2 and 9 divided by 2, you'll see that. And you know that when you graph 2.5, you just need to get between 2 and 3. Okay, don't need to be any more precise than that. Just get between 2 and 3. So we got what? We got 2.5 comma 0. That is going to be right here. 3 comma 1 is going to be right there. 4.5 comma 2, again, I'm going to go halfway between 4 and 5 along the x-axis, along with the y equal to 2 there. And then finally, 7 comma 3. Let me scoot this over a little bit. That's going to be right there. And you can see there, sure enough, it looks like that same basic shape that we had right here, doesn't it? It's starting to, let me move it up. It's starting to materialize into that same basic shape, isn't it? Okay, so please remember, you guys, the graph starts here. There is no arrow here, all right? That's what makes it different from all these other graphs. The square root graph actually has a starting point. Okay, so don't extend this any further than that. So since this point, you can tell that based on this shape here that this is the starting point here based on where these points are going. And so make sure it starts at this point right here. Do not put an arrow there or don't make it go down more. It starts there, okay? And then we just have one arrow on a square root graph, just one arrow. And you can see it has that same basic shape there. It's okay if it's a little bit shorter, okay, not as long as this. What's important is that it's the same basic shape. It's got its arrow, okay, all that stuff that it should normally have for that particular shape. Okay? All right, you guys, number 9, since we have absolute value in that one, all right, just like in the last one we had radical, and so we use the radical x function. Since we have absolute value, we are sure enough going to use the absolute value of x function. So let's take a look at that one a little bit more closely here. And let me go ahead and write down that we're going to use that up here as well. So I'm going to use absolute value of x. Now, once again, we have a situation where since it's the absolute value of x, all right, if since you're doing absolute value of x, you need to ask yourself what is being taken the absolute value of. Okay, just like in the last problem, if you're doing square root of x, you got to ask yourself what's being square rooted. If you're doing x squared in the first 7 problems, you got to ask yourself what's being squared. Since you're doing absolute value of x, you now have to ask yourself, what are we taking the absolute value of now? Well, the thing we're taking the absolute value of now is negative 1/2 x plus 4. Let me write that down 5 times here if I can get that squeezed in here. All right. And I don't think I can. Let me move the thing that where I just stated that it was absolute value. Let me move that. Okay, that way I have room for one more up here. There we go. Now we'll have enough room. Okay. Now, what are the original 5 numbers for the absolute value graph? The original 5 numbers are the same as they were for the parabola, the x squared. It's negative 2 to 2. Let me put those in there. And then we will solve those 5 equations right there. That will lead to, again, the new x's, and then we'll do the new y's there. As you can see, I kind of ran out of room there to write that, but as you guys know, after we do the equations, we then have the new x's and then the new y's. So we know basically how we're writing this out now. In order to get x by itself, though, you have to subtract over the 4 and then divide out by negative 1/2. But remember, when you divide by a fraction, it's the same thing as multiplying by the reciprocal. What is the reciprocal of negative 1/2? It is negative 2 over 1, which is the same thing as negative 2. So what we do then is we subtract the 4 first, like I said, and then we multiply by negative 2 because that is the reciprocal of negative 1/2. So let's do that on all 5 of these. Negative 2 minus 4 is negative 6. If we multiply that by negative 2, we get positive 12. All right, let's do the same thing on the other 4 here. Negative 1 minus 4 is negative 5 times negative 2 is 10. 0 minus 4 is negative 4 times negative 2 is 8. All right, 1 minus 4 is negative 3 times negative 2 is 6. And finally, move over the 4, we get negative 2 times negative 2 is 4. Now that we have that, we need to plug in these 5 numbers into the final function here. Plugging in 12. Remember, when you multiply by negative 1/2, you're just basically cutting the number in half and changing the sign of it. So negative 1/2 times 12 would be negative 6. Plus 4 is equal to negative 2. Please remember, just like with radicals, you guys, we need to do the inside of an absolute value before we calculate the absolute value. Okay? Radicals and absolute values work in the same way like that. And then we do the subtraction that's outside of it last. So, because subtraction comes after radicals and absolute values, always has. Negative 6 plus 4 was equal to negative 2, but remember, you got to take the absolute value after you calculate the inside of the absolute value. So the absolute value of negative 2 is 2. So the whole thing here, the absolute value is equal to 2, and then 2 minus 1 is 1. Let's do that again. Plug in the 10 into x, we get 10 times negative 1/2. Cut that in half, that's 5. The negative makes it negative 5. Negative 5 plus 4 is negative 1. But then you take the absolute value of negative 1, that's equal to 1. And finally, 1 minus 1 on the outside there is 0. The 8, when we plug it in, we get negative, we cut the 8 in half, it's 4. That gives me negative 4 plus 4, which is 0. Absolute value of 0 is 0. 0 minus 1 is negative 1. And then the last two here, we just calculate it the same way. It's going to be negative 2 and negative 3. Okay. Now, let's plot that. As you can see there, I'd like to be able to graph these normally without changing the scale here so you can see how it's all spread out, but it just won't fit. So what I'm going to do, that's okay. What I'm going to do is I'm going to change the x scale. Remember, you don't have to change both the x and the y. If you want to just change the x-axis without doing the y-axis or vice versa, you can do that. Okay, so I'm going to keep the y's the same. They'll be the normal 1, 2, 3 scale. So with that in mind, I get 12 comma 1 is right here. Okay, 10 comma 0 is right here. 8 comma negative 1 is right there where the 8 is sitting. Okay. The 6 comma negative 2. Oh, I'm sorry. I made a mistake there. I apologize, you guys. These are not negative 2 and negative 3. They are... This is what happens when you don't do your work. Okay, so I just realized that there. Let's go back, okay, to those last two problems, and you'll see why those are not equal to those two numbers I just erased. If I plug in the 6, I get 6 times negative 1/2 is negative 3. Negative 3 plus 4 is 1. Absolute value of 1 is 1. 1 minus 1 is 0. Okay. And finally, if I plug in 4, I get 4 times negative 1/2 is negative 2. Negative 2 plus 4 is 2. The absolute value of 2 is still going to be 2. And then 2 minus 1 gives me that. So plotting those now, 6 comma 0. And then 4 comma 1. And you can see here that a shape that's similar to this is developing. Or, sorry, I need to pull that up here for you. There we go. Let me zoom out a little bit. There's a lot of stuff I want you to see here all at once. There we go. Okay. So now you can see here that there's a V shape developing. Make sure that when it's absolute value, it's V shape. When it's x squared, in other words, the parabola, one of those types, then make sure it looks like a U shape where it's smooth. So V shape means you have that sharp turn. U shape means it is smooth. So let's make a V shape where it has that sharp turn, okay, right where this point is at the bottom. Okay, and if it's turned upside down, then that point would be at the top where it suddenly changes direction. That's how the problems work with absolute value. Okay, if it's going upward, then the bottom thing, the bottom point is where it changes direction. If the thing had been flipped upside down, like an upside down V, okay, then it would be the top point. where it would change direction. So make sure it changes directions at that point. All right, so that is number 9. We got just a couple more to go here. All right. In number 10, for the very first time, we see something not to the second power, but to the third power. All right. And so that means that we're going to base this off of the x to the third function that you see on your graph there that we have. All right. Okay. But here's the thing, though. Once again, let me zoom in there. Once again, the thing that is being, and let me back up again, just like we did before, if you're doing, for example, again, square root, then you got to ask yourself what's being square rooted. If you're doing square, x squared, then you got to ask yourself what's being squared. That's how you decide what this thing is right here. Since we're doing x to the third, you have to ask yourself what's being taken to the third power. Well, it's the x minus 1, isn't it? And so I am going to write down x minus 1 5 times, because the original x to the third graph that's on, let me bring it up here for you. The original x to the third graph right here is going to be, it's going to have these 5 basic numbers on it: -2, -1, 0, 1, and 2. Same as the x squared graph. We're going to use those same ones again. That's going to give me my... Oh, whoa, I got those backwards. Sorry about that. And what 5 new x values do we have? All right, what 5 new x values are we going to get here? All we got to do is add the 1 over to get the x by itself, right? And so, what do we get? -2 plus 1 is -1. -1 plus 1 is 0. 0 plus 1 is 1. And then I'll do the last 2 here. All right. And I'm sure that they're right this time, okay? I'm being more careful this time compared to the last problem. So then what are the y values that are going to go with that here? I'll go ahead. I know it's not going to hit this part, so I'll go ahead and use this part here to write those down, as long as the graph doesn't go in there. So if I plug in -1, I get -1 minus 1 is -2. -2 to the third power is -8. -8 times 2, because multiplication comes after exponents. -8 times 2 is -16, but then plus 1 is going to be -15, right? Okay. And then we do that same thing with the other 4 numbers. Plug in the 0. You get 0 minus 1 is -1. Cube it, it's still -1. Times 2 is going to be -2. -2 plus 1 is -1. Plugging in 1, I end up getting 0 cubed is 0. Times 2 is still 0. Plus 1 is 1. Plugging in the 2, let's see, I get 1 to the third is 1 times 2 is 2. And then plus 1 is 3. And then finally, if I plug in 3, I end up getting, to make a long story shorter, let me just do it. It's going to be 17. All right. So let's plot those. And as you can see, we got a couple of big numbers there, don't we? So what I'm going to do is I'll change this to going by 2s here on the y-axis, since it's the y numbers that get so big. So I get 10, 12, 14, 16, 18. There's 18 up there, and so 17 is going to be just before that. And then -15 then would be what? It would be 2, 4, 6, 8, 10, 12, 14, 16. So it'll be just before that. So let me start plotting these. The x-axis will still stay on the normal 1, 2, 3 scale here, where the marks are just 1, 2, 3. Negative 1, negative 15 is where? That is right there. As I said, this is negative 16 right here. Okay, so that's negative 15. 0, comma, negative 1 is right here, halfway between 0 and negative 2. 1, comma, 1, remember, that is right there because the y's are by 2's, and so it's halfway between 0 and 2 there. 2, comma, 3, right there. And then finally, 3, comma, 17, all the way up here. And so you can see here that a shape is developing that is similar to, as I zoom out, a shape is developing here that is similar to this shape right here, where it kind of goes like this. Same thing here. Let me just start to draw it, and then I'll color it in darker in a minute. So it's kind of going like this, right? Okay. Like that. Put your arrows on both ends. But can you see how that's similar to this here? All right, it's just that same type of shape. All right. Okay. And so there you go. All right. There we go. Okay, one more to go here, you guys. Again, we're back to square root again. All right, we got a square root in the function. It's got a linear expression in there with just the x being multiplied by a constant, and then we're subtracting a constant. So it still fits in that description of something where you can use your 5 basic, oh wait, what am I doing here? I'm sorry about that. I'm thinking like it's a smaller problem right here. Okay. So we're going to use what? We're going to use f of x equal to square root of x on this one, aren't we? Because of the square root function. Okay, so we're back to this one right here. All right. Now, since we're using square root of x, we have to once again ask ourselves, what's being square rooted? What's being square rooted is x plus 1. And so we write out x plus 1, this time 4 times, because remember we said when you're doing square roots, all right, you just need the 4 numbers here, not 5. 0, 1, 4, and 9. 0, 1, 4, and 9. Okay, so let me plug those in. What 4 numbers does this lead to here? What are my new x values right here? They're going to be, if you subtract the 1 over, you get negative 1, 0, 3, and 8. And then finally, okay, if we plug in the negative 1 and all these other numbers as well for the new x's, what do we get for the new y values? Plugging that in, we get, remember, you got to figure out the inside of the square root before you figure out the square root. And square roots come before multiplication and subtraction. So the inside of the square root is going to be 0 when I plug in negative 1. Square root of 0 is 0. 0 times negative 2 is still 0. And then when we subtract, 0 minus 5 is negative 5. Let's keep going. Plug in the 0 there. 0 plus 1 is 1. If I take the square root of that, it's still 1. Square root of 1 is 1. 1 times negative 2 is negative 2. And then negative 2 times 5, or negative 2 minus 5, rather, is negative 7. Next. The 3 plugged in, we get the square root of 4. Square root of 4 is 2. 2 times negative 2 is negative 4. And negative 4 minus 5 is negative 9. And finally, if I plug in the 8, I get square root of 9. Square root of 9 is 3. 3 times negative 2 is negative 6. And negative 6 minus 5 is negative 11. Let's plot these. As you can see here, these numbers get kind of big, and so again, I'm going to change my scale here on just the y-axis because it's just the y. Oh, well, the x's are kind of big too, but we can get the 8 in here. Let me squeeze that in. I can do like, there's 8 right there. We can squeeze that in still. 6, 7, and 8. But I'm going to change this to 2, or actually, excuse me, negative 2, negative 4, and negative 6, negative 8, negative 10, and finally negative 12. All right, with that in mind, let me zoom in there. Let's plot those 5 points. What do we get? Or those 4 points. Negative 1, comma, negative 5 is going to be what here? Hold on just a second, you guys. Excuse me. Okay. So that's going to be what here? That's going to be right here. And, excuse me. I put the negative 1 in the wrong, I put it in the wrong place there. Let me move these over to this side here. Negative 2 and negative 4. Okay. But negative 1, negative 5, excuse me, that is going to be right there. Because the y now it's got to be between negative 4 and then the next mark down is negative 6. All right. So there is negative 5 right there with the negative 1 for the x part. Okay. All right, now 0 comma negative 7, that is right here. 3 comma negative 9 is all the way over here. And then 8 comma negative 11 is right there. So you can see how it really stretches itself out. You might be wondering, well, wait a second here. How do I don't see, that doesn't look like this, you guys. Okay. But does that mean that it couldn't still be that? Let me zoom back in a little. There we go. Remember I said that this shape right here, or any of these shapes we're looking at in the basic graphs, they could be flipped upside down. Okay, so I want you to imagine this thing getting flipped upside down, all right? And notice it kind of has that thing here where it flattens out almost. And so it looks like this thing right here got flipped upside down. But I can understand how you still have some uncertainty. So I want to assure you of something here, all right? You might be wondering, is this really where the graph starts? You know, like, remember we talked about with radical function, it has a starting point, and this point right here is a starting point for the basic graph that I'm pointing at here. If I flip it over, how do we know where that point that it starts at, how do we know where that ended up? So here's how you know, okay? That point right there came from x equal to 0 in the original graph. It came from 0, 0 right here. So, that means that since it came from x equal to 0, you just have to go straight across over here, and then whatever point the 0 led to straight across here, that's the point where it's going to start. So that means that negative 1, negative 5 is where the point starts at, or where the graph starts at. So let's draw a shape that looks like we flipped the radical graph upside down here, and you can see that that's exactly what this is. It looks like we flipped it upside down, all right? But we now can be confident that it started right there because the 0 is where it started in the original graph, and so whatever is straight across from that is where it will continue to be as far as the starting point is concerned. Okay, so there's the final graph right there. Let me pull that back out there for you. Okay, so that concludes our discussion on these special types of graphs here, where they are a transformation of one of those 5 original basic graphs from section 2.6. Okay, have a great day, you guys, and let me know as usual if you have any questions.